Whew, I'm also tired. More about phylogenetic calculations. Guess what? I did start the video. Okay, so I'm going to kind of back up a little bit and talk a little bit more about Bayesian analysis, and then continue talking about Bayesian analysis now. And again, just to remind you, maximum likelihood and Bayesian are essentially calculating how well a tree fits, or the likelihood of a tree in the same essential way. We're both using likelihood to do this. We're using similar algorithms. We're using a matrix of costs for each change that we could possibly have. And the difference really between Bayesian and maximum likelihood is how we determine confidences. Where maximum likelihood, we're using bootstrapping to estimate confidences in each of the branches. Bayesian, we're sampling the same tree space. We're not changing the tree space by resampling the data and finding a new tree every time. We are just sampling one tree space and using all these sampled trees to figure that out. So we're using these simultaneous searches of tree space, and this is several different, I'm going to kind of fly through this because I talked about this on Wednesday, but we have n number of chains. So each chain is a different search through tree space. So essentially, if I come back here, this would be one chain. This is one chain through tree space, one search. And we have so many runs, so we're actually doing a set of chains so many different times. And those different runs are independent. And I'll talk about one of the things that makes them independent in just a moment. And what we're doing is, instead of going until we find the best spot, instead of like moving around until we find the peak in there, we're going to move around for a certain number of generations. So this should be familiar with to you after doing this yesterday. You set a certain number of generations or a certain number of moves through tree space you're going to make, and you let the algorithm run for that many. And then with MrBayes at least, if you're using it in the interactive mode like we were, it tells you how close those chains have gotten. Ideally, you want them all to have converge on the same answer. And so it tells you, in terms of likelihood, what is the separation between those different chains. And you can assess that, and if you've gotten to a low enough what's called split frequencies, we can determine, or we can decide to stop the run or continue the run. So we're not going until we find a peak. We're going for a certain number of generations. Now this makes sense, again, because we're not just trying to find that one best tree, we're trying to sample a lot of different trees around through this tree space. And because of this, we are moving in such a way where we're not moving in a greedy fashion. We're not moving in such a way in which we always take the better. If we move to a better tree, we always take that and never take one that moves to a worse tree. There is a certain probability, depending on this heated parameter, how likely it is that we are to accept a worse tree or move to a lower space in tree space. Now this helps us from getting stuck at some local maximum. What you want to be able to do is move around somewhat and keep sampling tree space. And the heat of the chains allows you to do this. So the hotter the chain is, the more likely it is to move downhill or accept those. And essentially all this does then is you're in a spot in tree space, you sample the next tree, and imagine you go down, and depending on how much worse that is, how less the likelihood is, or lower the likelihood is of that particular tree, depends on what is the likelihood of you calculating or accepting it. So if you were going down a very steep cliff, and it's much less likely, you're very unlikely to accept that tree and move that direction. If you're just going down like a slight little incline, you are more likely to accept that tree and move that direction. Is that making sense so far? Okay. And as we go along, as we are moving through tree space, we are sampling trees. So this is one of the things that you set up when we were setting up our parameters. In fact, let me go look at. Is this our lab? Yeah. So right here, when we were setting up our run, and essentially MCMC, this stands for Monte Carlo Markov chain. This is essentially the process that we're using to move through tree space. And the number of generations equals 1,000. So we started out just doing 1,000 generations, really short. And then we set the number of chains and the number of runs that we were doing to 2. So the number of chains is how many chains per run, and the number of runs is then how many independent searches we're doing. Now, these are independent because the way that we use runs is that we have 2 different heats for chains. We have a heated chain that is hotter than the rest of the chains. And these, only one can be heated at a time, and that which one is heated will switch. So sometimes one is heated, and you'll move through tree space, and that one moves more liberally through tree space, and the other ones are colder. And so instead of moving more liberally, those are more methodically working up tree space. And then randomly, every so often, which chain is the heated one will switch. And now that one gets to move more liberally, and then the other ones are moving kind of more conservatively. Each run only has one heated chain, and so that's why we have kind of the number of runs there. Print frequency is then aligned with coming up every so often. Some their computers were throwing up lines really quickly. You couldn't actually see the individual ones very well. Other people's it went very slowly. What it's doing is printing out statistics, which I'm going to talk about in just a little bit. Is printing out statistics of the searches every so many generations, and this is how many generations between prints. Between it prints out those statistics, and then the sampling frequency is how many generations are we moving before we sample a tree and keep it for our final statistical analysis. And then once you get that going, you just type in MCMC and that gets it all going. Is there any questions on that? So every so many moves that we set in there, the sampling frequency, we're sampling trees. And then we discard, when we actually go back to do the statistical analysis, often what happens is, let's go back to this little illustration of tree space. You're going to start somewhere random in tree space, and then you're going to work up to the top of the hill. And then what Bayesian does is he'll keep moving around this top of this hill, sampling trees for as many generations as it can. It'll move down the hill a little bit depending on how hot the chains are, but when it becomes the cold chain again, it'll move back up kind of to the top, so it keeps sampling around in the top of tree space. But here's the thing, when we run the statistics, we want to get an idea of the distribution of, or the shape of tree space in the best area. And then we're going to calculate our tree, our final tree, based on kind of all these sampled trees that we got. The problem is we didn't start in the best place. We started down here in the valleys, and we had to work kind of up to the best spot. So what we do is when we begin to analyze all these different trees that we've sampled, we don't want to include all this working our way up into kind of the better regions in our statistics. And so this is what we call the burn-in. We discard a certain number of the first of the sampled trees because they are very likely not in kind of the optimal region for our optimal areas of tree space for our calculations. So if we look again back at what we did, we ran these 2 commands here. SumP, so this is summing the probabilities of all the trees that we found. This is essentially going through and, okay, we've sampled all these trees, let's summarize them now. The SumP does that, and then what we did here, is you can either use an absolute or a relative burn-in. Absolute saying, I want to discard this number of trees that we sampled first, a relative burn-in being, I want to discard the first so much proportion. We did a relative burn-in, and we want to discard the first quarter of trees that we sampled. We're not going to use those because, again, we're just moving in. Then the SumT summarizes all the topologies of all the trees, so all the branching patterns of the trees that we found, into one kind of consensus tree. And again, we do the exact same thing. We discard the first 25% of the trees that we found because we don't want to include those into our calculations. And then just this, the con format. There's several different formats of trees that you can make out of MrBayes. It actually turns out you have to use the simple format for it to read well into R, so that's what we did. Okay. So, like I said, these sample trees then we use then to calculate the best tree and also the branch confidence. So we're doing it both to estimate then the branching pattern, then also the confidence that we have in each of those branches. And we're doing this, and this is where it gets its name Bayesian, is we're using Bayesian analysis or a Bayesian statistical approach to calculate what the tree should be. So I will very briefly describe how Bayesian calculates in a very non-mathematical sense. So the whole kind of idea behind Bayesian statistics as opposed to frequentist statistics, which is what you guys learned going through biostats and things that we've talked about even earlier in this class, have traditionally just been frequentist statistics, where essentially what you do is you just sit down and you look, okay, what is the probability of obtaining my data given the null hypothesis, right? So we have some null hypothesis of no difference, and we ask the question, what is just the probability of getting this data given if the null hypothesis is true? And you either then accept or reject the null hypothesis, also called null hypothesis significance testing. Bayesian statistics works slightly differently. What you do is you make a hypothesis and you can assign a certain prior probability to that hypothesis. And you can do this a number of different ways in which you're assigning the prior, but for the moment, we've just assigned some prior probability to that. Then you gather data or evidence either for or against that, and essentially what you do is instead of actually assigning a probability of a hypothesis just based on this evidence, now this evidence is adjusting this prior probability to get you another probability. Now, there's actually a relatively simple mathematical formula that goes into how you do this, and then it becomes wildly more complicated as you apply it to different systems. However, that being said, I'm just going to describe this kind of in loose terms, because I don't want to spend a ton of time on it. So really this is how this mimics how you assign probabilities to things in real life. Let me describe how that works. Imagine I brought you an old woman, and there is an elderly woman right here next to me. And as I do this, you automatically in your head have a range of probabilities of different characteristics of her, just because you know things about people in our society. So imagine she looks 70 to you, and I told you, this person is my grandmother. And you'd be like, okay, that's great. And you would say the probability of that, the probability that you would assign to that is relatively high. That's because the prior that you had that she is somebody's grandmother was relatively high already. You had additional evidence that she is my grandmother, and you probably had there's some probability that that was the case already. I mean, you probably wouldn't say this person's Kurt's grandmother, but it's possible. And then you use the evidence to assign a fairly high posterior probability, because we're just modifying that prior based on this evidence. I haven't given you much evidence. I haven't given you birth certificates. I have not given you any genetic data. I haven't given you much data. There is no, I've just told you that. I've not given you much evidence, but you would probably tend to accept it fairly readily because the prior probability that you assign to that is relatively high. Now imagine I have that same woman here. I said, this is an NFL football player. That same evidence all of a sudden is not worth you assigning or accepting that proposition anymore. It has nothing to do, the evidence is not different at all. What's different is the prior probability that you assigned to just automatically in your head to that being the case without even thinking about before I said that. You assigned it very low. Now, all that being said, I could give you enough evidence you would probably accept that at some point. I could say, well, hold on here, she's just a kicker, so she's never getting tackled really. I could like give you her card. I could give you like video of her being drafted, maybe her playing in games. I mean, there is some amount of evidence that I could give you. Like probably not. That probably actually doesn't exist. But I mean, in hypothetically, there could be evidence that I could give you that would eventually get you to the point that you would accept the hypothesis. That the probability, the posterior probability would be high enough you'd be like, okay, I'm accepting that, the hypothesis. But the evidence has to be significantly higher for that claim. The reason for that is that the prior probability that you assign to that is much, much lower. In the end, given enough data, your prior doesn't matter. Given enough data. But when you have limited data, the prior does matter. This is essentially how, and there's an entire field of statistics that is dedicated to Bayesian statistics. Essentially everything that you've ever done in statistical analysis. There is a Bayesian equivalent to that works this way. And actually, there's a lot of evidence that this works a lot better. For instance, when we are looking at new medical treatments or new drugs or other things like this, if you use a purely frequentist approach and a null hypothesis significant test approach, there's a lot of ways in which those predictably go wrong often, that we will begin saying, oh, such and such does this and works, when it really probably doesn't. And Bayesian statistics don't fall into that trap nearly as often as frequentist statistics. Are you raising your hand?
Yeah.
Okay, yeah.
So how do you come to a prior probability?
Okay, so that depends a lot on everything. On what area you're in. Oftentimes you can use prior studies, first principles on what is being studied. In the case of this, in the case of phylogenetics, we like to use what are called uninformative priors. They're essentially saying everything's equally possible. We have no, and so the idea then is you have sufficient data, hopefully, that your priors don't matter too much. And so what we do then is we have a tree topology, something like this. A completely uninformative tree that tells you nothing. Everything is equally related. And then we can start from that topology and then modify that topology based on additional evidence. And then also the distribution of probabilities of each of the branch support is also uninformative and essentially equally likely. And so we start with these priors and we begin modifying them based on evidence. Okay? This will come up later as we're looking at all of our trees and looking at how they look different. And some of that is because our data was kind of messy, and when we have low signal, we get weird things. Like when they fail in predictable ways. We'll come back to that based on this. Are there any other questions on that? That's kind of a very surface and hand-waving sort of explanation for something that's a lot more well-defined, but hopefully gives you the idea. So we start with this, a prior something like this, then we use all the trees that we have sampled as the evidence then to come up with, or then called posterior probabilities. And when you find Bayesian branch support, oftentimes they are called the Bayesian posterior probability for the branch support. And if you have a bootstrap, it's just the bootstrap value usually. And so this is what branch support is called in the respective of things. So also this just BPP or just BV or sometimes BP, the bootstrap percentage. Any questions on that so far? And again, when we calculate this, we're discarding the first so many samples because those are not useful, because we're just, or tend to be actually the opposite of useful, not like make things worse. Okay, let's talk a little bit about the outputs that you were getting from MrBayes as well. So as you were going, you were getting something like this coming out onto the terminal screen, and there'd be new ones added down here and keep pushing this up and up and up. This is just some output of one that I was running yesterday for. So I'm running the trees, our trees again, and what I'm doing is I'm running them not just with your data, I'm running them also with all of the data of that large data set you were working with in week 6. And so it has all of those representative haplotypes in there as well. So instead of having 20 taxa, it now has like 150 taxa in there. And we should get better resolution with that. And then I am going to have you do an applied assignment with that tree output at some point. So you'll be able to see what that is. But this is one of the runs associated with that. And I did the same way. What I did is I had 2 runs with 2 chains each. What you have, this first column is the number of generations that you're on. I had a print frequency again of 100. So every 100th generation, we're getting these output again. If they were flying too fast across your screen and you couldn't really see what was going on, generally what you would do in that case is set the print frequency down so it's printing less frequently. But this is going every 100th, and you see I'm right now up to like 200,000. I'm actually not that high, but it's going kind of slowly because of the bigger data set. And then what you have now is all of these now are the likelihoods, the log likelihoods of the calculated, that have been calculated for the trees it sampled at that generation. So at the 285,600th generation, the 4 trees that got sampled here had these 4 log likelihoods. These first 2 before the start are the first run, the 2 chains. The second 2 are the second run and their 2 chains. You'll notice that one of them has parentheses in each run, the other one has brackets. The bracketed one is the heated chain. So this is the heated chain, this is the cold chain, heated chain, cold chain. And one other thing that you'll notice is that they change every so often. So for here, you see bracket, bracket here. This is the heated chain up top here, and then it switches to this one. So now this one is the heated chain, this one's the cold chain. And so that is now how they're moving through tree space, and then off on your right-hand side, this is the amount of time left. So that is kind of what you are looking at as we go through this. So each one of these, as you look, this is a different search. So each one of those essentially lines up with one different line like this of searching through a tree space. After you ran the sum p, you got something out like this. This is one that you got a lot of different outputs. And that, what? Go back. This is one of the outputs that you got. And so we had a burn-in of so much, so we discard that burn-in. You see, this is the first generation after the burn-in started. And then this is one of the burn-ins, or this is at the end of the entire thing. So I went 3 million, about 3.5 million. Oh, I guess one other thing here. Again, you have split frequencies here. You see my split frequencies are like horrible even after 200,000 generations. It's not even close to being done here yet. We're waiting for this to get down. So essentially what we're waiting for is all of these to converge on similar likelihoods. So this is just looking at the deviation of the likelihoods, okay? And so we're hoping that they all converge on something of similar likelihood. Now all that being said, if they're on 2 different peaks, you could still get your split frequencies down, but they're on 2 different peaks if they're of similar height. This gives you another kind of output of that, and what you want to see here is each one of these numbers now is one of the runs. So this is run 1 and run 2 down here. This is run 1, run 2, and this is the log likelihoods that they found for those runs at the sampled at a whole bunch of generations here. What you want to see here in this little graph output is that it's essentially flat, that there's not a trend up anymore. And what that tells you is that we're sampling in an area where we're not still moving into better and better likelihoods, that we've essentially reached the top of the mountain. And we've been sampling around the top of the mountain, so we're not increasing and getting better and better. What we are doing is just essentially moving through a semi-flat space, hopefully at the top of the hill. So that again tells you that not just that they have converged, you can see that they converge because the 1s and the 2s are kind of all, there's not like 2 is consistently at a different height than 1. But we also can tell that we are what's called, we've reached stationarity, in that we are not increasing our likelihoods anymore, or decreasing our likelihoods that it's flat. So that's another thing that tells you you have gotten to the end of this analysis. Another thing is it gives you this when you run the sump as well. A couple things to look at here is the ESS. This is the estimated sample size for each of these different parameters. So we can look at if we sampled enough for that all of our parameters for the trees have kind of converged as well. The estimated sample sizes, the recommendation is that that is over 200, and this is. And then this is also another kind of diagnostic. I'm not exactly sure what it is. It's supposed to be close to 1. And so there's that as well. So then, if you look at all of those, generally all of that has reached that. There's oftentimes one other thing that you check is convergence and topology. I'll come back to that later. So this is what we came out with. I've modified it a little bit after applying it to make it look a little bit higher. So this is not very resolved. So remember what this is called right here, where we have a whole bunch of things coming off of one branch point? At all? Anyone? It's called a polytomy. So you have lots of different branches coming off of one single branch. So it's not bifurcating. You have a lot coming off of essentially one node. And this means that the tree is not very resolved. We haven't actually arrived at anything that really well resolves the tree. Despite getting our split frequencies down. So like our split frequencies converged, but our tree still is not very resolved. However, there's a couple good branches. Like Mo and Leah, you guys come out with really strong, very good. And Ryan Robinson, not here. Who's person 18? Someone who didn't fill it out. Okay. I can probably narrow it down. There's only 2 people that didn't fill in one, so I could probably figure that out. And then down here, Elliot Berger and person 17, which I think are the same sequence on accident. Jenna and Jordan, which also are not. Like if you played well, apparently you don't show up. Arthur's, and then Taylor Callan and Matt Hansen. Okay, you guys are here. So hey, long lost brothers here as well. So I'll come back to this. We're going to talk about this and talk about this compared to the maximum likelihood tree in just a few moments. But how could we improve this analysis? Well, one good way is to increase the number of independent runs that we're doing. So we did 2 runs. Probably, if I were to run this again, increase this to 3 or 4 independent runs. What that does is that gives you more sampling in the area. You could also run it more generations. And running it more generations, you could look for better convergence. So we got there's 3 different ways. So the split frequencies was the one that you're looking at as it comes out. We come to similar log likelihoods. Okay, whatever. And the parameters is that thing at the end when it spits out that is showing that we can kind of look at. We can look at the estimated sample size. Our parameters have good sampling. But the other thing that we can look is we can look at convergence of topology. Or essentially what we're looking at is if all of our branching is coming out the same over and over and over again. So what we look at there then is, you can't actually do this in MrBayes. There are other programs that you can dump in your output tree files. Did you notice that MrBayes spit out a lot of different files? Yeah. Those are useful actually. So the only one that I had you guys look at was this one, the con.tree file. If you come down here actually to There's a run2.t and then there is a run1.t as well. This is where is stored all the individual trees that were sampled the entire way through and their likelihoods. So if you open this up, actually that's 6 megabyte text file. Maybe I should have done that. 6 megabyte text files are kind of crazy. Yeah, this is like 300,000 some odd. A little bit because instead of having the names of all the taxa inside the tree, we assign numbers to all the taxa, and that just sticks the numbers inside the parenthetical, so we can actually store an entire tree in a rather condensed format down here, and it helps to store lots of trees that way. Cuts down on the size significantly. But otherwise, it's just actually, do I have AWT up? Yeah. And so you can take these tree files and stick them into other programs like this one called AWT and use diagnostics, for instance, like this compare chart where essentially is you have run 1 and run 2, you take 2 different runs, and you're comparing the branch support for specific branches. If they come out on a line, that means your 2 runs have arrived on similar topologies. If this is more of a cloud and wide and kind of scattered all over the place, your runs in topology have not converged very well. Another thing that you can look at is branch support cumulative probabilities, and this helps you determine burn-in. So what you'll notice here is this is each of your branches, and this is the branch support it gets. And you'll notice that they change for a while, but then they kind of level out. This gives you a good idea of where to cut your burn-in off, because all of this is crazy. And now beyond like about 1 million generations or 10 million generations, then we're having pretty consistent topology after that. Okay. So we can also look for better convergence by topology and run more generations until we have good convergence based on topology. So there's all these different ways that we can figure out all of our runs converging on the same answer. And we might have to run it longer until eventually they do. Okay. So here are the 2 trees that we ended up with. Is this basically what everyone saw for both your maximum likelihood tree and your Bayesian tree? Anyone see anything significantly different? Yeah. Does the branching pattern of these look similar? In rough sense, no. Does anyone want to offer a reason why the 2 might be different based on methodology of how we went to about comparing them? Or how you determine these trees? Okay, let's talk about that then. So with maximum likelihood, how we determine this is we use our actual data set and we find the best tree based on that data, right? And then we keep that, and then what we do then is we go through and then run this with a whole bunch of bootstrap resampled data sets to figure out the branch support. And then we figure out then how many of those trees that we bootstrap resampled and made contain the branch that occurs in this one that we found with the non-resampled data. So what we have here is, and actually this is the default output of PhyML is actually to give you the number of trees. So this was at 100, so this is exactly the same as a %, but if we did this at 1,000, then essentially you would just add 10 onto each of these, or times each of these by 10, essentially, and that'd be about what you would get. And you have to divide them all to get the percent by the total number that you would have done. But, so, like, look at this one. This is Leah Dan, Maureen, Person 18, Ryan Robinson, Sarah Anderson, Kalia, and Cedric. You came out with the normal data. You guys came out together. But that branch was not returned on any single one of the bootstrap resampled ones. Never did that come out again. So there's a 0 there, which means we don't have very much support for that. Whereas we look at some other ones, we have Person 18 and Ryan Robinson came out on 80 of those resampled ones. Jenna Thomas and Jordan came out on 71. So some of them are well supported. Elliot came outside, and Person 17, who's Elliot? You should just like sign things Person 17. Yeah. Or Elliot Berger, comma, Person 17. In fact, you could just do P17, and people would think it's like PhD, but it's like P17 is like better. I like that. What's that?
I got my PhD at 17, so it's...
Oh, exactly. Yeah, that's exactly what it is. If you get your PhD by or before 17, it's a P17 rather than PhD. I like it. Okay, so we have these things that are absolutely poorly supported. Okay. What would this branch then look like if you came up with a similar branch in a Bayesian analysis? Okay, let me just ask this. What is the likelihood of coming up with a polytomy like this in a maximum likelihood search? You probably won't do it. Okay, so the difference here, one of the big differences here is with Bayesian, we start with a tree that looks like this, and then we get evidence to make it look different. Okay? And so we need a decent amount of evidence to start putting together this branching patterns. And so if we don't get sufficient evidence, what we get then is something that looks like this. It just says, I can't change it from this. I don't have sufficient evidence to say it's any different than this. And so if you have very, very poorly, if your data does not support like any particular branching pattern very well, you will get something like this where it's just like a lawn. It looks like shoots of grass. Actually, if I turned it, though. Whereas this, we have went through with one particular data set and found the best tree, and that best tree is going to have topology to it. It's going to have some sort of branching pattern to it because that's how we're searching for trees. We're searching for bifurcating trees. And then we go through and we bootstrap resample, and then we find out that all these branches are like, oh, those branches are crud. They don't work at all. So with maximum likelihood, you will get a fully resolved tree because of how we search for the tree. Even if the branches are horrible, you will get a branching pattern. And then you'll find out later that, oh, when we did the bootstrapping, then we found that there's no support for that branch whatsoever. This branch in Bayesian comes out like this. They just say, no, we can't take anything here. We're just going to take this and all the way back. I have no evidence to clade these two together, so I'm just going to draw them back. And this that just gets drawn back. And this, nope, that's only two, that gets drawn back. And this three, nope, draw that back. So it doesn't clade these things together based on such poor support, unlike maximum likelihood. It'll just leave it completely unresolved. Okay. Are there similar branches that come up with strong support in both of these? Does anyone see any? Yes. Say it again and louder.
Me and Mo.
Yes, you and Mo. You and Mo come out together pretty strongly. Okay, so here's a 0.901, and here it's 74. So these are posterior probabilities. These are percentages that they came out. Which one assigned it higher probability? The Bayesian. Okay, let's look at a couple others. Like, for instance, Elliot Berger and Person 17. Okay, let's skip that one for now. Taylor Kill and Matt Hatson, a 0.87 here, and over here it's 57%. Okay. Over here, let's see here, we have Jordan and Jenna, 0.8, basically a 0.81, and here a 71. And then Julie is in with both of those over here, 0.57 and a 48. If we're counting these all as percentages, which tends to be higher? Bayesian, yes. This is a consistent trend. Bayesian tends to give you higher confidence values. There's a reason for this. It actually turns out, empirically, bootstrap, it's hard to know what it actually means. Because we're resampling this data, and it's not quite the same as bootstrap resampling with confidence intervals, just a bag of numbers like we were doing earlier in the quarter. It's really hard to know how to actually interpret that. And so what we've done is people have gone back and they've done simulations, and they're like, okay, at what bootstrap values can we be 95% confident that it comes out? Like, a tree with this value is right this many percent of the times. And there's been studies that people have done with simulations where essentially they start with one sequence, and then they just randomly mutate it in certain ways, and then kind of like make the tree, and then try to calculate so they know what the topology of the tree is. They try to back calculate it. Or we've looked at things where we really actually know the descendants pattern really, really well, like for instance purebred dogs or something else like this, where we know, like it's been papered for like hundreds of years or something like this, and we know exactly what the branching pattern is, and then we can take their DNA and then work back and see how well we can get that. It actually turns out that a 70% bootstrap confidence is right about 95% of the time. So this isn't like a p-value or the inverse of a p-value. This actually is a lot stronger than just the value itself purports. Bayesian, because we're doing this in a different way, and we're actually using this, like we're sampling lots of trees and we're applying a statistical, essentially a model to come up with this. This is a pretty much right on. This is about 90% likelihood of being correct. And other branching pattern like that. That is fairly right on. So this and this are actually telling you about the same thing. You notice that this is 0.9 and this is 74. That's about the same confidence both ways. It doesn't look like it, but Bayesian and maximum likelihood, those values have to be interpreted slightly differently. If you're just looking at them one for one, Bayesian is going to tend to be higher, and that's what you expect. And bootstrap is going to tend to be lower, but you will say that a branch is well supported down to about 70% bootstrap value. Kind of a nuance here. You'll also notice that, kind of coming back to this, we don't have any bootstrap values below 50%. If it doesn't get at least a 50%, they generally don't. Most summing algorithms don't even count it as being a branch. They'll just go back to being. Here's an interesting one. Taylor Kelm, Matt Adds, and Ashlyn Gazal come out together in here really nicely, strongly clated, 74%. So that's a good branch. Does that come out together well in the other tree? I'm seeing people shaking their head no. Who votes no? Who votes yes? Wait, what was no and yes now? I don't know. Do they come out well together? No, yes. I don't even know what people vote. You probably don't know what you vote either. I don't know. It's early in the morning. Okay, so actually, they do come out well in the Bayesian tree. They come out together. They don't look like it, but you do come out together. You come out together with really high probability, actually. The thing is that it's rooted in these two trees are rooted in a different place. The left-hand tree is rooted on Elliot. It's rooted right here in this tree. Actually, right here in this tree. So we decided to say Elliot is the root for this tree, and they decided to make Ashlyn the root in the other tree. So Elliot, yeah, you two are the random roots to decide. I think you got rooted in the MrBayes tree because it wants to do the first one, and you are alphabetically the first person in the class. So I think it just grabbed you as being the root. So you can be very confident that you are the first alphabetical person in class. That's awesome. But really, look at this. What this is saying now is that there's a 0.999% probability that all of these people come together, who are not Taylor, Matt, and Ashlyn, together without one of those three people in that group. The reciprocal of that is that those other people group together, Ashlyn, Matt Hansen, Taylor Kelly, group together and don't go out into that group with 99% probability. Does that make sense? That these two clade into two distinct groups 99% of the time. So the three of you guys come out as a group very often. It's just that we decided to root this tree on Ashlyn, so that's how it goes. So actually, this branch right here is returned well here as well. It's just not. This doesn't look like it from this rooting pattern. Now that being said, if I had more time on this section of the class, we get into programs that actually let you just like click, like you can load this tree up into like a GUI that you can then just click certain people and reroute the tree on that person. And you just click on nodes and it flips the nodes and you can kind of like change things. And, yeah. Yes?
So is the Ashlyn relation to the Taylor and Matt, is that the top value on the Bayesian chart?
No, so that one is this value right here. Because essentially what this value is saying, you're trying to imagine it as like an unrooted tree.
Oh, I got
If
it.
this was this line coming out and then going to those three, it's essentially saying that this value is this group and this group clading is two different groups. Does that make sense? So this is the value of Ashlyn, Matt Hansen, and Taylor, but then also of this group coming out together. Only 1% in those trees, it decided that based on their likelihood and other things, that these guys have a very high probability of coming out in their three and everyone else in the class coming out together. Make sense?
Yeah.
So yeah, you can, all of these you can read as reciprocal. Is person 18 and Ryan Robinson came out together, we have a very high probability that those two come out together, but the equally likely probability that everything else comes together as a group as well without them. And it depends on where you root it, which way it's natural for you to look at that. Okay, just a couple real quick things. So this is kind of just a couple thoughts on phylogenetics before we take off. Just really quick, because we're leaving this, we're going on to transcriptomics next week, which will be fun. But oftentimes phylogenetics gets used as a really powerful tool, but as one component of larger and more interesting studies. And it really seems to reach its like flowering, interesting potential as a part of something else. Like, so for instance, I talked about very beginning of this, how we can determine spreading pattern of disease based on phylogenetics. But also we can couple this with like spatial information as well, so you get phylogenetic information plus spatial information, and you can tell really well the geographic distribution or spreading of things in space as well. So like for instance, we figured out where flu is coming from all the time. Like where does flu come from animals into people, because it's most often zoonotic. Where does that jump out? We found out with a combination of spatial data and phylogenetic data. Also, we figured out, like, this is just a couple studies I could remember off the top of my head. Where in the world were cats domesticated? Northern Africa, it turns out. But, so where were cats domesticated? We figured that out with a combination of spatial data and phylogenetic data. So, we can do really cool stuff figuring out history in geography. Where did things move, and where did people move, or where did viruses or other infectious agents move, or where did animals move, based on a combination of spatial data and phylogenetic data, which is really, really cool. We can also look at adaptations in populations using phylogenetics. So one thing I will be doing, hopefully, I'm hoping to submit some grants for this short period of time, is can octopuses adapt to high CO2 in a short period of time, like in individual lifetimes or in a couple generations, or does this take long generations to adapt to it? Because it turns out that the octopuses in Puget Sound are really well adapted to high CO2 because they've been living in there forever. But if I took another octopus and put it there, could it adapt in like a couple generations? That's hard for me to do with actual octopuses because I can't raise a couple octopuses in generations in lab. That's really hard to do. And no one's gonna let me just grab octopuses from other places of the world and dump them in Puget Sound. That's generally frowned upon. Like intentionally inputting invasive species. But this is something I could look at with phylogenetics and looking at the combination of phylogenetics and then geographic distribution of adaptiveness to high CO2. Really interesting to do. We can also do something called ancestral characteristic reconstruction, where we can look back in history and try and determine all these different nodes, what were their characteristics like? What was their genetic sequences like based on good sampling of all their descendants, which is another really cool thing that we can do with phylogenetics. So really, I'm giving you some of the tools to like begin looking at phylogenetics, but I wish I had like another 2 or 3 weeks or an entire quarter just to talk about phylogenetics, because at this point, like the applications of this are just so cool across the board, and I barely got you to the point where like, hey, we can make a tree, but what can you do with that now? It's like super awesome. Anyways, with that, I will say adieu for the weekend, and I will see you on Monday where we will begin a new topic. Enjoy your weekend, rest and relax. Talk to you soon.